Now you can hear me. All right. So hello everyone. How's everyone doing? Yeah, we're gonna continue with Zig today. We're gonna well, today is gonna be memory and allocators. So last time we finished all the control flows, structs, modules, and types and whatnot, so we have some kind of understanding. But before we go on and do memory allocators, let's actually get back to our Ziglings, okay? Because during the first ever episode, we just did some of the initial ones. I think we went all over to number 8. And you can see that next one is like, if, else, and for loops and whatnot. So let's quickly do some of them. As a warm up and a refresher what we were doing last time, because it's been a few days and, not practicing a language every day actually hurts a lot. So we'll see how, all the reminders are here until we get to the point where we get something new, and then we're going to switch to the actual memory, because you can see that we have pointers and whatnot soon enough. And these are teeny tiny. So yeah, let's get to it. Let's start with number 9. Now we get into fun stuff, starting with the if statement. If true, else, bam. Zig has the usual comparison operators, such as all those. Okay, so super, awesome. The important thing about Zig is Zig's if is that it only accepts Boolean values, okay? It won't coerce numbers or other types of data to true and false. That is super awesome, because I always hated the fact that somehow 1 is supposed to be true. And I don't know, just sometimes you see this thing. Is it a Boolean? Is it a number? And just makes you wonder. Okay, so constant type standard. And what do we have here? I wonder if I should pull this repo or something. Okay, I pulled something. Readme and build, and that's all that changed. Okay, I guess they updated the way it's supposed to work. Alrighty. So how do we fix it? This is just, please fix this condition. If foo comp time is 1. We want our program to print this message. Only the first one, right? Foo is 1. So foo is 1. And I guess that should work, right? So we're gonna go and do 0, 0, 8. Wait, 9. Oops. Foo is 1. There we go. Okay, so that was easy. Another if statements are also valid expressions. So const foo is this: if a, 2, else 3. All right. So we've got this, and we have our discount, which is Boolean true. Use an if else expression to set price. If discount is true, the price should be 17, otherwise 20. So we have basically if discount, then if the discount is true, should be 17, else should be 20. And the value of these should be inferred as 0.8 because we have the typeset here. With discount, the price is bam. So let's run the number 10. Oops, not 19, 10. There we go. Awesome. Next. Number 11. Zig while statements create a loop that runs while the condition is true. This runs once at most. So while condition, const condition, blah, blah. Remember, so it runs at, this runs once at most. Oh, because we have condition true and then we set it to false. Yeah. Remember that the condition must be a Boolean value, and that we can get a Boolean value from conditional operators such bam. Okay, so we have the standard stuff. We have some kind of number n, which is 2, and please use a condition that is true until n reaches 1024. Okay, so n is, well, n is less than until it reaches. So when it reaches, it's no longer correct, right? Current number, we have n, and double the n. Okay, all right. So it's gonna print all the way to 512, right? We save it and we run it with 11. There we go. Up to 512, and at the end, n is, there we go. Perfect. Gosh, these are so easy. While 2. The while statements can have an optional continue expression, which runs every time the while loop continues, either at the end of the loop or when the explicit continue is invoked. We'll try those out next. Yep. Okay. So while condition, and then we have our continue expression. So example, foo is 2, and foo is this, and basically, continue expression is basically what we do every iteration, right? And then do something there. Beautiful. See if you can rewrite the last exercise using the continue expression, right? So we had until is less than 1000. Please set a continue expression so that we get the desired results in the print statement below. So first of all, this was supposed to be 24, even though it doesn't change anything right now. So we were supposed to double it, right? Yeah, n double. So we do n times equal double, and that should be it. That should be literally it. Let's do 12, and there we go. We have the same result. It's 1024. Beautiful. Yeah, as simple as that. Yeah, I like this little thing. It's fun. 13. The last two exercises were functionally identical. Continue expressions really show their utility when used with continue statements. So while condition, we have continue expression, and if other condition, continue. Yep. The continue expression executes every time the loop restarts, whether the continue statement happens or not. Yep. So we have 1. We want to print every number between 1 and 20 that is not divisible by 3 or 5. So basically we have until 20, and we increment 1 by 1. And the percent symbol is the modulo operator, and it returns the remainder after division. Awesome. So if it's divisible by 3, as in the division by 3 yields 0 when it comes to no remainder, then we have it divisible. So we want to print every number that is not divisible. If it's not divisible, and here it's divisible, we just continue and we skip it. And we're gonna do the same here. Okay, when it's divisible by 3 or 5, we continue. Otherwise, we print it. And between 1 and 20. Okay, so we start from 1 and we finish with 20. Okay. Sig run 13. There we go. 1, 2, 4, 7, 8, 11, 13, 14, 16, 17, 19. Beautiful. Alrighty. 14. We're going fast to that. You can force a loop to exit immediately with a break statement. Bam. If some other condition break. Continue expressions do not execute when a while loop stops because of a break. Yep. So standard import standard, whatever. So 1, oh dear, this while loop will go forever? Yeah. Please fix this so the print statement below gives the desired output. Result, we want 4. Okay, so we should finish while the n is 4. So if n is 4, we just break. And that's it. Yeah. There we go. Next. For loop. Behold a for loop. For loops let you execute code for each element of an array. 4 items, and we have the iterated extracted element in the between the pipes. And what do we need to do? We have story, which is H, H, S, and H. Okay. I guess maybe that means something for writers or something. And then we print a dramatic story. And for, I guess, the scene inside a story, we want to print out H will be happy, S will be sad, and will be neutral. Okay, so we know what these mean. And the end. Know that for loops also work on things called slices, which we'll see later. Also note that for loops have recently become more flexible and powerful 2 years after this exercise was written. More about that in a moment. Okie dokie, so so we take story and we extract all the elements of the array, which will be our scene. Well, where did the pipes go? VS Code is behaving funny. All right, that's it. There we go. Beautiful. Next. For loops also let you use the index of the iteration, a number that counts up with each iteration. To access the index of iteration, specify a second condition, as well as a second capture value, right? Because we can iterate over multiple things at the same time. You can name item and index anything you want. I is a popular shortening for index. The item name is often the singular form of the items you're looping through. Okay, so we've got some bits. Let's store the bits of binary number 101 in little endian order. Last significant byte or bit first. Yeah, so it's basically stored backwards. Okay. Now we'll convert the binary bits to a number value by adding the value of the place as power the 2 of each bit. Okay. See if you can figure this, the missing pieces. So I guess we'll be going over bits and their index. Know that we convert the usize to U32 with intcast, a built-in function just like import, and we'll learn about these properly later in a later exercise. So basically, inside our loop, we take our bit, right? And now the I. So this is supposed to be the I, the index. And they want to go from 0 to whatever it is, right? I presume from 0, right? Blah, blah, blah. And so this will be our index as a U32. Then we go place value will be power. So with a power, standard math power. So we got just standard math power. It takes a type that we operate on. The value to whatever the I don't even know the proper names for it in English. The number and its power. Base number or something, I guess, base number, and the actual power. And value is increased by this times that bit. So the place value. So if we start from 0, 2 to the power of 0 is 1, to the power of 1 is 2, and so on. So that will be perfect. Yep. From 0 to whatever it was supposed to be. And yeah, I guess that's it. Sig run 016 and yeah, 13. There we go. Does it mean that it's supposed to be as mentioned in the previous exercise, for loops have gained additional flexibility since these early exercises were written. As we'll see in later exercises, the above syntax for capturing the index is part of a more general ability. Hang in there. Yeah, so that we can actually pass however many we want to iterate over at the same time. And I believe as long as they have exact same length, it will be fine. I don't know what's going to happen if they have different lengths or unknown lengths. It's a good question. Okay, let me just message my wife that it would be nice if she was able to turn on the AC because it's hot in this little box. Let's see. Alrighty, next one, quiz. Quiz time again. Let's see if you can solve the famous fizz buzz. Players take turns to count incrementally, replacing any number divisible by 3 with the word fizz, and any number divisible by 5 with the word buzz. Okay, let's go from 1 to 16. This has been started for you, but there are some problems. So import import it. Wasn't it import like this? std. Oops. Not capital. Yep, looks like that's it. Function main. Not whole word function. fn, and I think this should be public function. There we go. Now we can actually run it. Variable I, which is 1. Stop at 16. What kind of loop is this? A for or a while? This is a while loop. While I is less or equal, stop at, and we increment I every iteration. Then we go on. If divisible by 3, then we print fizz. Divisible by 5, we print buzz. And if not divisible by 3 and not divisible by 5, we print this. Otherwise, we print out comma. Okay, as in this will be the number itself, right? So it will be I in this case. We print the comma. Double click selects everything. It's like it can't really comprehend the syntax, and this will be an integer, so we don't need to put anything here. And that will be the comma. So yeah, let's see what happens. Zig run 017. Fizz, buzz, fizz. Yeah, this looks good. We have extra comma at the end, but whatever. I mean, we can do additional if I is not stop at, right? If it's not stop at, then we will print it. Otherwise, we simply don't care. What the hell is going on with this thing? Constantly something wrong. There we go. And this should fix it, right? There we go. We don't have the comma at the end at the cost of performance, but it's okay. Alrighty, next functions. Let me close all the other ones. Wait, there's a magical close all others. Yeah. Functions. We've already created lots of functions called main. Now let's do something different. Function foo takes u8, returns it to the foo function above, takes a number and returns number that is larger by 1. Note the input parameter n is and return types are both u8. So the new function deep thought should return the number 42. Okay, see below. So bam. So we call it here, but notice that this is declared below. Okay, lovely. So answer is this. Answer to the ultimate question is 42. Of course, please define deep thought function below. We're just missing a couple of things. One thing we're not missing is the keyword pub, which is not needed here. Can you guess why? Well, because we're within the same module, which is basically the same file. So it'll be function, deep thought, and it returns. In this case, they want u8, so that this is, expecting that. And yeah. $18. And there we go. Next. Now let's create a function that takes a parameter. Here's an example that takes 2 parameters. As you can see, parameters are declared just like any other types, name and type. Bam. So we have number 8, number U8 and is lucky Boolean. Okay, so we have this function, the main that will print powers of 2 is, and 2 to the 1, 2 to the 2. Okay, so simple power. That we're just wrapping the math one. Okay. Please give this function the correct input parameters. You'll need to figure out the parameter, name, and type that we're expecting. The output type has already been specified for you. So yeah, this is the output type. The input type, I could basically say anything at this point, but I'd presume they are supposed to be the same. So let's do power, which will be U32. Oh, my number, sorry. Yep, there we go. Standard of power, this and that takes a numeric type and 2 numbers of that type. So that can correspond to the type and returns a power of B as the same numeric type. Okay. Alrighty. Save. Zig, run. 19. Done. Okay, next quiz already, and then we're gonna get to errors, which we haven't touched yet. Although we learned about defer, we learned about switch, unreachable, not really, if error, and enums. We did something about enums, not pointers. Yeah, then it's like an entire mix of stuff that we did and did not do. But there are only, what, 100 exercises, and we're already at exercise 20? So that's not bad, right? So let's finish this quiz and we're gonna go to learning the new content. Let's see if we can make use of some of the things we've learned so far. We'll create 2 functions, one that contains for loop and one that contains while loop. Both of these are simply labeled loop below. Okay, so our main function will say my numbers, so we have a list of U16. Okay, print powers of 2. And we give it entire list. Okay, print powers of 2. All right, and then we just print them. So these are 2 loops. You won't see this every day. A function that takes an array with exactly 4 U16 numbers. This is not how you would normally pass an array to a function. We'll learn about slices and pointers in a little while. For now, we're using what we know. This function prints but does not return anything. So print powers of 2. So it's numbers, takes the numbers and returns print powers of 2. It expects we don't, wait. We're not even putting it anywhere. Wait. Oh, this is the bug print. So for the numbers in here, we return void. I mean, yeah, I don't think we learned about void yet, but maybe. So this will be loop, some kind of loop, right? This is a for loop. So for each number n, we're gonna print the 2 to the power of whatnot. This function bears a striking resemblance to 2 to the whatever in the last exercise, but don't be fooled, this one does the math without the aid of the standard library. Okay, function 2 to the whatever, and I guess it also returns U16, that's the goal, I guess, and then we'll be basically multiplying it times 2, while n is larger than the number, we increase it, bam, 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 until we fall out of here, and we'll return the total. W16, bam, 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 and I guess that's it. Zig run 020. And okay, we got our 4 numbers. Yep, they look right. Okay, done. We're all done. So let's move on from exercises because next one is about errors and we're not theoretically equipped to know them yet. So bye-bye Ziglings. We can switch to probably our test one, which is just bunch of nothing good right now. I'm just gonna leave one debug print as a hat to have a quick template to mention it. And that's it. Alrighty. So, memory and allocators. Finally, we're getting into some fun stuff. And when do we learn about error handling? Wow, and 10 something tells me we're gonna do those Ziglin's exercises a little bit sooner. Today's live stream won't be long, so maybe in an hour and a half I'm gonna finish. We'll see how far we get through here. This is probably pretty long, so we'll see how that goes. In this chapter, we'll talk about memory. How does Zig control memory? What common tools are used? Are there any important aspects that make memory different or special in Zig? You will find the answers here. Computers fundamentally rely on memory to function. This memory acts as a temporary storage space for the data and values generated during computations. Okay? Without memory, the core concepts of variables and objects in programming languages would be impossible. So the concept of memory spaces. Every object that you create in your Zig source code needs to be stored somewhere in your computer's memory. Depending on where and how you define your object, Zig will use different memory space or a different type of memory to store this object. So we're creating, lists and whatnot. I mean, by lists, I mean arrays. I wonder if it's possible to just move an array to heap or something. We haven't seen any hint of that syntax yet, so that's curious. Each type of memory normally serves for different purposes. In Zig, there are 3 types of memory, or 3 different memory spaces that we care about. They are global data register, as in the global data section. Okay? So this will be all our static stuff that is read-only and, little snippets of text that your program stores directly in the executable, precompiled and other precompiled pieces of data, I would say. Then we have stack, which is what we were dealing with so far, and heap, which is, out there. We can get more of it whenever we want. So compile time known versus runtime known. One strategy that Zig uses to decide where it will store each object that you declare is by looking at the value of this particular object. More specifically, by investigating if this value is known at compile time or at runtime. When you write a program in Zig, the values of some of the objects that you write in your program are known at compile time, meaning that when you compile your Zig source code, during the compilation process, the Zig compiler can figure out the exact value of a particular object that exists in your source code. Knowing the length or the size of each object is also important. So the length or the size of each object that you write in your program is, in some cases, known at compile time. Exactly. The Zig compiler cares more about knowing the length or the size of a particular object than to know its actual value. But if the Zig compiler knows the value of the object, then it automatically knows the size of the object, of course. Because it can simply calculate the size of the object by looking at the size of the value. Therefore, the priority for the Zig compiler is to discover the size of each object in your source code. If the value of the object in question is known in compile time, then the Zig compiler automatically knows the size or length of this object. But if the value of this object is not known at compile time, then the size of this object is only known at compile time if and only if the type of this object has a known fixed size. Yep, so let's say we define an array. We don't know how large yet, but I mean, what exactly is in there, but we know that it will store 5, U32, right? So at this point, we know, okay, to be 5 of this kind of value, we know how much memory to reserve, right? In order for a type to have a known fixed size, this type must have data members whose size is fixed. This type includes, for example, a variable size array in it. And then this type does not have a known fixed size because this array can have any size at runtime. For example, it can be an array of 2 elements or 50 elements or 1000 elements, etc. For example, a string object which internally is an array of constants, of constant U8 values, as in this thingy, right? We don't specify how large it is, has a variable size. It can be a string object with 100 or 500 characters in it. If we don't know at compile time which exact string will be stored inside the string object, then we cannot calculate the size of the string object at compile time. So any type or any struct declaration that you make that includes a string data member that does not have an explicit fixed size makes this type or this new struct that you're declaring a type that does not have known fixed sizes at compile time. Wow, this is like a really detailed explanation of very simple concept, at least in my opinion. In contrast, if the type of this struct that you are declaring includes a data member that is an array, but this array has known fixed size, like 60 instances of U8, which declares an array of 60 U8 values, then this type or the struct that you are declaring becomes a type with a known fixed size at compile time. And because of that, in this case, the Zig compiler does not need to know at compile time the exact value of any object of this type. Since compiler can find the necessary size to store this object, store this object by looking at the size of this type. Let's look at an example. In the source code below, we have two constant objects, name and array, declared. Because the values of these particular objects are written down in the source code itself, Pedro, and the number sequence from 1 to 4, the Zig compiler can easily discover the values of these constant objects during the compilation process. This is what known at compile time means. It refers to any object that you have in your Zig source code whose value can be identified at compile time. So we have input length, whatnot, usize, and this. So we have constant name, Pedro. So this is like 100% known the length and the value of each element of the array. We know everything that can be about this specific value, right? And this here is the same thing. We see that this is exactly for a list, an array of 4 elements. And hey, the underscore just means that we ask compiler to count them for us. So compiler again knows everything about it. While here, not really, this could accept anything. The other side of the spectrum are objects whose values are not known at compile time. Function arguments are a classic example of this. Because the value of each function argument depends on the value that you assign to this particular argument when you call the function. For example, the function input length contains an argument named input, which is an array of constant U8 integers, right? It's impossible to know the value of this particular argument at compile time. And it also is impossible to know the size or length of this particular argument. Because it's an array that does not have a fixed size specified explicitly in the argument type annotation. Yeah, exactly. We just don't know what size it is. Could be 1, could be 0, could be million elements. So we know that this input argument will be an array of U8 integers. But we don't know at compile time its value and neither its size. This information is known only at runtime, which is the period of time when your program is executed. As a consequence, the value of expression input.lang is also known only at runtime. This is an intrinsic characteristic of any function. Just remember that the value of function arguments is usually not compile time. Usually. However, as I mentioned earlier, what really matters to the compiler is to know the size of an object at the compile time and not necessarily its value. So although we don't know the value of the object and in which the result of the expression input len, at compile time, we do know its size because the expression input len always returns the value of type uSize, and the type uSize has known fixed size. Exactly. Okay, really? That was that long? Wow. Okay, so let's get to actual meat of the thing, because this whole chapter so far is confusing. So global data register. I presume the global data register is only for values that we know not only the size, but we know exact value, so that it can be just stored in here. The global data register is a specific section of the executable of your Zig program that is responsible for storing any value that is known at compile time. See, any value that is known at compile time. And John is asking, what is Zig? Why instead of C? Zig is, imagine it, modern C, where it's harder to make mistakes. And why instead of C? Because my goal is to learn not just a programming language, but delve deeper into understanding the basics of computers, as in how to work with memory, how maybe send some, low level stuff, and maybe some like system architecture and whatnot. And with Zig, I know that I will be spending more time actually understanding the concepts and learning them, rather than hunting down which pointer I forgot and basically fighting C and the fact how easy it is to make bugs in C. So that's the main goal. And at the same time, Zig is apparently fun and has actual build system that you don't have to slap on. That's like random. It's just simpler, And hey, Zig is now often used as the main C compiler for many people because it's just easier to use. But yeah, that's my opinion for now, at least. Alrighty, so every constant object whose value is known at compile time that you declare in your source code is stored in a global data register. So that's what I was saying. Also, every literal value that you write in your source code, such as the string, this is a string, or the integer 10, or Boolean values such as true, is also stored in a global data register. Whatever. Honestly, you don't need to care much about this memory space because you can't control it. You can't deliberately access it or use it for your own purposes. Also, this memory space does not affect the logic of your program. It simply exists in your program. Yeah, so basically, if you're going to compile it, a program or whatever, you can open it up, as in not execute it, but just open it up and find all those strings and some other values within that source code. Not source code, within the compiled executable, which is often a fun way to, reverse engineer something or inspect or, I don't know, fix something, make a crack for some kind of software. Yeah, it's a fun little thing to do. And then we have stack versus heap. If you're familiar with systems programming, I am not, or just low-level programming, in general, you probably have heard of the duel between stack versus heap. Yes, even in a little bit higher level languages, you still need to be mindful. If you're doing this, or you're doing that, you often have the concept of like value versus reference types, right? So value types like integers, whatnot, you usually think of like, oh, these will exist on some kind of, on a stack. While things like maybe classes, objects, often strings in some languages, will exist in a heap. And you kind of have that differentiation, even though you're working in some kind of higher level language. Yeah, one of those things is like, let's say in C#, when you're deciding should this be a struct or should it be a class. Struct will be possibly on a stack while copied every time, therefore, while object will be always passed by a reference, so it's going to work a little bit differently. Of course, behind the scenes, magic happens. A lot more different things, optimizations and whatnot. Even Zig does that, but you know, the overall behavior can be predicted. Okay, so these two different types of memory or different memory spaces, which are both available in Zig. These two types of memory don't actually duel with each other. This is a common mistake that beginners have when they are seeing X versus Y styles of tabloid headlines. These two types of memory are actually complementary to each other. So in almost every Zig program that you ever write, you will likely use a combination of both. I will describe each memory space in detail over the next section. But for now, I just want to establish the main difference between these two. Types of memory. So in essence, the stack memory is normally used to store values whose length is fixed and known at compile time. In contrast, the heap memory is a dynamic type of memory space, meaning that it's used to store values whose length might grow during the execution, as in during runtime, of your program. Yep, lengths that grow during runtime are intrinsically associated with runtime known types of values. In other words, if you have an object whose length might grow during runtime, then the length of this object becomes not known at compile time. If the length is not known at compile time, the value of this object also becomes not known at compile time. These types of objects should be stored in a heap memory space, which is a dynamic memory space which can grow or shrink to fit the size of your objects. Yep, simple. Okay, so stack. And the stack is a type of memory that uses the power of the stack data structure, hence the name. A stack is a type of data structure that uses a last in, first out, as in LIFO, mechanism to store the values you give it to. I imagine you are familiar with this data structure. But if you're not, see the Wikipedia page or the Geeks for Geeks page are both excellent and easy resources to fully understand how this data structure works. So the stack memory space is a type of memory that stores values using a stack data structure. It adds and removes values from the memory by following a last in, first out principle. Again, a repeat of the thing that was here. What the heck? Every time you make a function call in Zig, an amount of space in the stack is reserved for this particular function call. Yep, a stack frame is being created basically. The value of each function argument given to the function in this function call is stored in this stack space. Also, every local object that you declare inside of the function scope is usually stored in the same stack space. Looking at the example below, the object result is a local object declared inside the scope and the add function. Because of that, this object is stored inside the stack space reserved for the add function. The R object, which is declared outside of the add function scope, is also stored in a stack, but since it's declared in the outer scope, this object is stored in a stack space that belongs to the outer scope. Yep. So basically, each function can be considered a little box on a stack. Whenever you call it, the box is created to kind of fit all the values that it's going to store, and operations happen on them, right? Yeah. I won't be going deep into that. It's obvious to me, and if somebody wants to study how stack works, Core Dumped, that's the name of the channel. Core Dumped is a great channel to go for that kind of stuff, although he has really in-depth explanations. YouTube.com. I'd say go and search for Core Dumped. There we go, and he has great videos. There should be one about stack somewhere, right? Da, 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 da. We might need to, there we go. Why is the stack so fast, right? And the size of your variables matter. So these two videos are something, and then you have a little bit about the heap. And I would say these are great videos. So I'm gonna share that in the chat if somebody's ever interested. If you're watching that after the stream, I believe you can still access the chat. So that's one thing, and I believe low-level learning also had something similar about, stack and how it works here and there in some videos, but I won't be searching for the specific one right now. Let's just move on. So any object that you declare inside the scope or a function is always stored inside a space that was reserved for that particular function in the stack memory. This also counts for any object declared inside the scope of your main function, or for example, as you would expect in this case, they are stored inside the stack space reserved for the main function. One very important detail about the stack memory is that it frees itself automatically. Yep, so when, let's say, you're in here, right? And then you're gonna call add. So what's going to happen is that those two values will be put on a stack as those, we need to make a frame that denotes start and end of the function. That's few values that needs to be created. Then it's going to put those two values as in kind of copy them in a stack, like, hey, this and that is something that matters. And then it needs to create room for this result. That's another thing. It does its calculation, saves to a specific spot what is supposed to be returned. And then it kind of goes backwards and it cleans this, cleans that, removes the other stuff. And by removes, it still exists there. It just moves like the pointer to where to in a stack it was. So in theory, you could read some stuff. In the previous, or I don't know, if number 2 or number 3, one of the live streams, we actually were able to create a list of elements on inside a function and then exit it and still read them. So yeah, that was fun. So you can do shenanigans, but most of the time you're being protected from them. And it clears automatically, so whatnot. And the amount of stack you get when starting the program is like limited. Like this is how much you get, and that's it. You can't get more, and that's why you have the Stack Overflow error. Alrighty. One very important detail about the stack memory is that it frees itself automatically. This is very important. This is very important. Remember that when objects are stored in the stack memory, you don't have the work or responsibility of freeing or destroying these objects, because they will be automatically destroyed once the stack space is freed at the end of the function scope. So once the function call returns, or ends if you prefer to call it this way, the space that was reserved in the stack is destroyed. And all of the objects that were in that space go away with it. This mechanism exists because the space and the objects within it are not necessary anymore, since the function finishes its business. Using the add function that we exposed above example, it means that the object result is automatically destroyed once the function returns. Exactly. Important, local objects that are stored in the stack space or a function are automatically freed, destroyed at the end of the function scope. So this same logic applies to any other special structure in Zig that has its own scope by surrounding it with curly braces. For loops, while loops, if-else statements, etc. For example, if you declare any local objects in the scope of a for loop, this local object is accessible only within the scope of this particular for loop. Because once the scope of this for loop ends, the space in the stack reserved for this loop is freed. The example below demonstrates this idea. So we have a constant, right? This, I believe, will just live not even on a stack. This will just live in the global memory because we know its size, we know its values, that's where it's gonna go. All we're gonna get is a pointer to it, stored inside of A. And then, this is supposed to be in a main loop, but nonetheless, this will be in global memory. So for A to A.length, we iterate over it, right? Our index I, so this is gonna be created, whatever, void or whatever it is, and we kind of exit this iteration and this gets wiped. It doesn't exist anymore. The moment we start next iteration, this will be created from scratch. So that's fun. And it's good to know that the curly braces, the little blocks, also kind of start and end the stack frame or whatever, the block. And this way we can, if we have to, actually reduce the amount of stuff that's stored in stack. So one usage for that I can think of is that, let's say you have some kind of recursive function that calls itself and then within itself calls itself and goes and go on and go on and go on. You might have some kind of more complicated things being calculated in that function, right? So maybe we can actually go into code and kind of mock it up, right? So let's say that we have a function like functions do recursive stuff, okay? And maybe we just give it one number and another number. And here I guess I need to specify types. So we're gonna U32, there we go. Whoa, A and B. I'm just putting in numbers. So we got A and B, right? And we expect that it's gonna return another U32, all right? So let's say that we have a function of this sort, right? But what it's gonna do is maybe here we're just gonna, do some stuff, which will be basically a lot of stuff. Maybe you will create a variable ABC that's maybe some kind of list, right? We don't know how many yet, or something from A to B or whatnot. Let's say creates a list of numbers. I'm not even using correct Zig syntax here, I don't care. But create something, another variable, and another variable, right? You create them and whatnot. What the hell? I'm just gonna put some of them here. And in between, you have a bunch of code sprinkled. And at the end, what you're gonna end up with is just two numbers, var A2 and var A3 or something, whatever. A1, A2. There we go. Wait, A2, B2. That's what I wanted. But you just created so much data in between, right? And the moment you're gonna call now the do recursive stuff, and you're gonna give it A2 and B2, right? And maybe all you need to do is at the end just to return, right? All you need to do is return from that. So what's gonna happen is, let's say in our main, we're gonna do whatever. We need to print value will be, and we just put it in here. So this will be our value, whatever, the thing that we return. So we can do constant, or in this case, whatever, variable value, which will be do recursive stuff, maybe from 1 to 100, right? So what's going to happen here is that the moment we start this, the room on stack will be reserved for all those variables, all of them, okay? And therefore, at this point, we're going here and we're like, oh, we need to create room for more of those. And then while this is calling, we're gonna do even more and more and more and more. And it just keeps taking up more and more and more space until it might get, if you have too many iterations, it might just decide, you know what, there's no more room in the stack, there's stack overflow. So I wonder to what extent one could do something, you know what, we're gonna move those two values that we want to eventually set and put them here, right? Maybe we're even gonna do them unset or whatever, undefined. I guess that's the keyword here, right? We don't know what exactly value it will be yet, but we can wrap our stuff in here and say, you know what, this is gonna be a block. And it's gonna do the calculations here. It's gonna say A2 is whatever and B3 is whatever, whatever, right? And we close it and it's supposed to clear of those, all those. So I'm just wondering how much does the function predefine space the moment it's being called, like all the space that it's gonna need? Or does it add it on the go and therefore remove it on the go? Because if that was the case, our recursive stuff could go here, then wipe it all and get leaner. By the time it's calling it, most of the data that would be taken up by the stack and just sitting there doing nothing is gone. So yeah, that would be fun. And this therefore also could be put maybe in there to just not be here. Huh. I guess that would be a good question to AI. Let's try it. Please look at this code. Incomplete for, it's just an example. Okay, we're gonna give it some code, okay? I'm learning about how stack works in computers. When I call the recursive stuff function, does it reserve room, or does it reserve room on the stack that's already predefined in size? Or does it increase, or does it whatever, add new values to it as it executes instead, right? I'm wondering if specifying an extra block in whatever that would clean up its variables make a difference here when function is called recursively many times. Let's switch to Opus. Let's let it actually think for a moment and we'll see, because something tells me that this maybe creates some stuff initially, but then it just keeps adding, and that would be great. That would be great. In the meantime, we can start reading, okay? So one important consequence of this mechanism is that once the function returns, you can no longer access any memory address that was inside a space in the stack reserved for this particular function, because the space was destroyed. This means that if this local object is stored in the stack, you cannot make a function that returns a pointer to this object. Exactly, we tried to do that and it kind of works, but it breaks because very soon your next executions will just destroy it. Think about that for a second. If all local objects in the stack are destroyed at the end of the function scope, why would you even consider returning a pointer to one of these objects? This pointer is at best invalid or more likely undefined. In conclusion, this is totally fine. It is totally fine a function that returns the local object itself as a result, because then you return a value of that object as in you copied it. But If this local object is stored in the stack, and you should never write a function that returns a pointer to this local object, because the memory address pointed by the pointer no longer exists. So using again the add function as an example, if you rewrite this function so that it returns a pointer to the local object result, this compiler will actually compile your program with no warnings or errors. At first glance, it looks like this is good code that works as expected, but this is a lie. If you try to take a look at the values of our object, or if you try to use this object in another expression function call, then you would have undefined behavior and major bugs in your program. Yeah, because we just don't know what there is, right? If we have our add and we return a pointer to the result, right? This is great. But the moment we call another function here, maybe define another value, it might already start overriding parts of this result itself. And therefore, when you give the pointer and actually read that value, it might be something different already. Yeah, most likely. And it will be something very strange. So this invalid pointer to stack variable problem is well known across many programming language communities. If you try to do the same thing, for example, in a C or C++ program, for example, returning an address to a local object stored in a stack, you would also get undefined behavior in the program. If a local object in your function is stored in the stack, you should never return pointer. So it's a repeat of the same thing. I guess these nodes are for people who are skimming and would just miss that. So this leads us to heap. Let's see if we got anything here. All right. So looking at your Zig code example, let me explain how stack allocations work for recursive functions. So stack frame allocation. When the recursive stuff is called, the entire stack frame is allocated at once with a predefined size determined at compile time. The compiler analyzes all local variables in the function, regardless of scope blocks, and reserves enough space for the maximum simultaneous usage. Oh no, right? So all these variables still count toward the total frame size. Oh no, what? That's too bad. So block scopes don't reduce stack usage. Oh no, so I was wrong. The inner block doesn't clean up stack space during execution. The compiler typically calculates total space needed for all variables across all scopes, may reuse memory slots for non-overlapping variable lifetimes as an optimization, and allocates the frame per function call. Ay. However, compilers can optimize variable slot reuse, tail call optimization, and optimize this reuse the same stack. Yeah. So better recursive pattern. For deeper recursion, consider the recursive stuff. Base case first, do that. Oh, just instead of having internal block, just call a function. Because a function will actually clean up after itself. So that's funny. Huh. So the blocks are purely for us to basically not have to worry about, oh, I still have this variable available and therefore I could introduce a bug. All right. Just call a function, a little bit more costly, but hey. All right. Okay. I hope this is true. I hope. All right. We are 1/3 through the whole thing. Wow. Okay. But what if you really need to use this local object in some way after your function returns? How can you do this? The answer is in the same way you would do this where a C or C++ program. By returning an address to an object stored in a heap instead. The heap memory has much more flexible lifecycle and allows you to get a valid pointer to a local object or a function that already returned from its scope. So heap. The important limitation of the stack is that only objects whose length size is known at compile time can be stored in it. In contrast, the heap is a much more dynamic and flexible type of memory. It's the perfect type of memory to use for objects whose size length might grow during the execution of your program. Virtually any application that behaves as a server is a classic use case of the heap. A HTTP server, a SSH server, DNS server, LSP server, any type of server. In summary, a server is a type of application that runs for long periods of time and that serves or deals with any incoming request that reaches this particular server. The heap is a good choice for this type of system, mainly because the server does not know upfront how many requests it will receive from users while it is active. It could be a single request, 5,000 requests, or even 0 requests. The server needs to have the ability to allocate and manage its memory according to how many requests it receives. Yep. Another key difference between the stack and heap is that a heap is a type of memory that you, the programmer, have complete control over. Yep, with stack we don't really have much control, at least not like a precise control, because things are dotted. It's compiler that kind of manages it mostly. So this makes the heap, well, with the heap we can just allocate and do whatever we want. So this makes the heap a more flexible type of memory, but it also makes it harder to work with because you, the programmer, is responsible for managing everything related to it, including where the memory is allocated, how much memory is allocated, and where this memory is freed. So unlike stack memory, heap memory is allocated explicitly by programmers and it won't be deallocated until it is explicitly freed. To store an object in the heap, you, the programmer, need to explicitly tell Zig to do so by using an allocator to allocate some space in the heap. In section 3.3, we will present how you can use allocators to allocate memory in Zig. So literally at the end. Wow, okay. All right. The majority of allocators in Zig do allocate memory on the heap. Majority, okay. But some exceptions to this rule are Arena Allocator and Fixed Buffer Allocator. The Arena Allocator is a special type of allocator that works in conjunction with a second type of allocator. On the other side, the Fixed Buffer Allocator is an allocator that works based on buffer objects created on the stack. There you go. This means that the Fixed Buffer Allocator makes allocations only on the stack. So I guess it reserves some amount of room in a stack ahead of time, and it allows it to just put stuff in there, take stuff out of there, and kind of manage out memory. Okay. All right. Summary. After discussing all of these boring details, we can quickly recap what we learned. In summary, the Zig compiler will use the following rules to decide where each object you declare is stored. Every literal value such as this is a string, or 10, or true is stored in the global data section. Every constraint object, const, whose value is known at compile time is also stored in the global data section. Every object, constant or not, whose length size is known at compile time is stored in the stack space for the current scope. If an object is created with the method alloc or create of an allocator object, this object is stored in a memory space used by this particular allocator object. Most of allocators available in Zig use the heap memory, so this object is likely stored in a heap. And Fixed Buffer Allocator is an exception of that. And the heap can only be accessed through allocators. If your object was not created through the alloc or create methods of an allocator object, then it is most certainly not an object stored in a heap. Oof, I'm glad we're finally done with this whole memory spaces description because it's like very, very, very repetitive. Come on, I will learn something new. Stack overflows. There we go. Allocating memory on the stack is generally faster than allocating it on the heap. But this better performance comes with many restrictions. We have already discussed many of these restrictions of the stack, but there is one more important limitation that I want to talk about, which is the size of the stack itself. The stack size is limited in size. The size varies from computer to computer, and it depends on a lot of things: the computer architecture, the operating system, etc. Nevertheless, this size is usually not that big. This is why we normally use the stack to store only temporary and small objects in memory. In essence, if you try to make an allocation on the stack that is so big that it exceeds the stack size limit, the stack overflow happens, and your program just crashes as a result of that. In other words, a stack overflow happens when you attempt to use more space than is available on a stack. This type of problem is very similar to a buffer overflow. For example, if you're trying to use more space than is available in the buffer object. However, a stack overflow always causes your program to crash, while a buffer overflow does not always cause your program to crash, although it often does. You can see an example of a stack overflow in the example below. We're trying to allocate a very big array of EU64 values on a stack. You can see below that this program does not run successfully because it crashes with a segmentation fault error message. So var very big alloc, so we do 1000 times 1000 times 24. So what? 24 million EU64 elements. And we don't even set the value, and then memory set, okay, very big alloc, I guess all the values we set to 0. So we 0 the whole thing. This is interesting. Let's try that. I want to see Stack Overflow. Alrighty. I've got a NAT here. Alrighty. So yeah, we're gonna do a very simple thing. We're just gonna paste in the code and see it crash. Save and zig run 000. Bam. Error, use of undeclared identifier value. Oh yeah, let's just comment this out. It didn't even compile. Segmentation fault, core dumped. There we go. It just couldn't. What if we're gonna do 10 instead? Still a problem. Just one? Oh, one just fit. So we're able to put in a million U64s, and that's pretty much it. Anything more, I don't know, 4 or whatever, it's just not enough, right? Oh, 4 still fits. How about 8? Segmentation fault. There we go. 7, probably still segmentation fault. Probably the 4 was the most. Yep. 5. Oh, 5 runs. Oh, this exact value. 6. 6 runs. So basically 6 million. Interesting number. 6.5? Nope. Oh, probably 64. And a fault. 63 will work. Maybe. Nope. Okay, never mind. It's probably some area is used by other stuff, like the zig itself. But okay, all right. This is kind of fun. So yeah, the moment you go into millions, you're screwed. Alrighty. So the segmentation fault error is a result of the stack overflow that was caused by the big memory allocation made in the stack to store the very big alloc object. This is why very big objects are usually stored in a heap instead of stack. Yep. So, okay, we're finishing. No, allocation section is long. It just looked like one little number, but not really. Okay, so let's finally learn about those allocators. One key aspect about Zig is that there are no hidden memory allocations in Zig. What that really means is that no allocations happen behind your back in the standard library, okay? In the standard library, you can for sure make it work if you want to in some other way. This is a known problem, especially in C++, because in C++ there are some operators that do allocate memory behind the scenes. And there is no way for you to know that. until you actually read the source code of these operators and find the memory allocations calls. Many programmers find this behavior annoying and hard to keep track of. But in Zig, if a function, an operator, or anything from the standard library needs to allocate some memory during its execution, then this function operator needs to receive as input an allocator provided by the user to actually be able to allocate the memory it needs. This creates a clear distinction between functions that do not from between functions that do not from those that actually do allocate memory. Just look at the arguments of this function. What is this function? Somewhere down here. If a function or operator has an allocator object as one of its inputs or arguments, then you know for sure that this function operator will allocate some memory during its execution. So, allocprint, I guess. We don't have any function. We're just calling stuff. All right. So an example is the allocprint function from the Zig standard library. With this function, you can write a new string using format specifiers. So this function is, for example, very similar to the function sprintf in C. In order to write such a new string, the allocprint function needs to allocate some memory to store the output string. Yep, because we're building it on the go, we don't know the size of it yet. That is why the first argument of this function is an allocator object that you, the user programmer, gives as input to the function. In the example below, I am using the general purpose allocator as my allocator object, but I could easily use any other type of allocator object from the Zig standard library. So variable GPA, which is standard heap general purpose allocator, we call it with nothing, and then we don't know what we do with that. I'm not sure what this is supposed to mean. So unless this returns some kind of type that we create here as an empty whatever. Not sure, very confusing. And we have constant allocator and we do GPA allocator. So we GPA dot allocator. Something tells me this is some kind of type. We're gonna paste it in a second to kind of inspect it. So allocator, we just get it from the GPA. And constant name Pedro. So this is constant, right? Constant output is try. Do that. I can do that as a constant. That's interesting. I guess because these are all constants. This will evaluate during compilation time, maybe. I don't know. But we have output and we do try standard format allocprint. We give it the allocator, then our template, and what to put inside of the first element. All right. And then we just print it out. There we go. And hello, Pedro. You get a lot of control over where and how much memory this function can allocate because it is you, the user or the programmer, that provides the allocator for the function to use. And this makes total control over memory management easier to achieve in Zig. So what are allocators? So before we do that, I want to see this. I want to see what the types will say. You indent, please. And we do not try. This will be standard debug print. There we go. So this thing returns debug allocator function. What? Debug allocator and parentheses. What the heck? Oh, look at that function. it returns a type, which is a function that takes comp config and itself returns a type. Okay. Debug allocator, but what debug allocator? Because I'm probably depending on if you're in debug mode or something else, you're gonna get a different allocator probably. And right here is the debug mode. So we get our debug allocator, right? And we get the actual allocator, like a more generic one out of it. What else can we do? GPA dot backing allocator. Buckets, large allocation, something. Large allocations, mutex, requested memory limit, total requested bytes, and can deinit and do other stuff. Very interesting. Or detect leaks, huh? Interesting. And this just returns an actual allocator. Okay. What if I remove those two? Then it's just a random type. Oh, so this returns a type. Okay, so that's exactly what I was expecting. This returns a type, and then here I create an object of that type. But the moment I create that object, somehow I get a type? I mean, a function? This is so confusing. Go figure. Something we don't know about yet. Alrighty, so what are allocators? Allocators in Zig are objects that you can use to allocate memory for your program. They're similar to the memory allocating functions in C, like malloc and calloc. See, alloc? So if you need to use more memory than you initially have during the execution of your program, you can simply ask for more memory by using an allocator object. Zig offers different types of allocators, and they are usually available through the standard heap module of the standard library. Thus, just import the Zig standard library into your Zig module with add import standard, and you can start using these allocators in your code. Perfect. Furthermore, every allocator object is built on top of the allocator interface in Zig. Interface, huh? This means that every allocator object you find in Zig must have the methods alloc, create, free, and destroy. So you can change the type. I'm so sorry, I'm constantly yawning. So you can change the type of allocator if you are using. But you don't need to change the function calls of the methods that the memory allocation and the free memory operations for your program. Yep, it's basically an interface, so we can swap them out quickly. No big deal. A standard thing. So why do you need an allocator? As we described, every time you make a function call in Zig, a space in the stack is reserved for this function call. But the stack has a key limitation, which is every object stored in the stack has a known fixed length. But in reality, there are two very common instances where this fixed length limitation of the stack is a deal breaker. First, the objects that you create inside the function might grow in size during the execution of the function, or sometimes it is impossible to know upfront how many inputs you will receive or how big this input will be. Yep. Also, there is another instance where you might want to use an allocator, which is when you want to write a function that returns a pointer to a local object. As I described in section 314, you cannot do that if this local object is stored in the stack. However, if this object is stored in a heap, then you can return a pointer to this object at the end of the function. Because you, the programmer, control the lifetime of any heap memory that you allocate, you decide when this memory gets destroyed or freed. These are common situations for which the stack is not good. That is why you need a different memory management strategy to store these objects inside your function. You need to use a memory type that can grow together with your objects, or that you control the lifetime of this memory. The heap fits this description. Allocated memory on the heap is commonly known as dynamic memory management, as the objects you create grow in size during the execution of your program. You grow the amount of memory you have by allocating more memory in a heap to store these objects. And you do that in Zig by using an allocator object. So the different types of allocators. At the moment of the writing of this book in Zig, we have 6 different allocators available in the standard library. Okay. The general purpose allocator, page allocator, fixed buffer allocator, and thread safe fixed buffer allocator. Wow, okay. Arena allocator and C allocator, which requires you to which requires you to link to libc. I guess this one is to specifically deal with C and whatnot, and let C manage its own memory, right? Each allocator has its own perks and limitations. All allocators except the fixed buffer allocator and arena allocator are allocators that use the heap memory. So any memory that you allocate with these allocators will be placed in the heap. Okay. Something tells me, something tells me that this arena allocator, because it pops up a lot for some reason, is that this allocator just doesn't allocate anything on its own. It just delegates it to a different allocator. But it might be something where this one is being stored on a stack and it kind of maybe pre-allocates larger amount of memory that something else can do. I don't know. Probably something of this sort. Okay. General purpose allocators. So the general purpose allocator, as the name suggests, is a general purpose allocator. You can use it for every type of task. In the example below, I'm allocating enough space to store a single integer in the object store number. Ooh, just an integer. So again, we create our allocator, right? There we go. Constant sum number is try allocator create u32. Oh, it's that simple. Just create me this. And I guess here it's a store number, but isn't it literally just a pointer to it or something? An allocator destroy some number. And if we try to get it here, it will be probably an error, right? Some number and whatever, because we already destroyed it. While useful, you might want to use the C allocator. So let me try that. I really want to see that. I want to play with it. All right. I'm gonna leave that down here because I don't know why. Oh, it reformats, so I can't even have room. Okay, so yep, there we go. Some number is a pointer to u32 value. So we can just give that pointer back and destroy it. Okay, and I guess the allocator keeps track that, hey, this pointer points to this data that then I can deallocate. Okay. Yeah, so I guess when I try to run this will crash because some number is not available anymore. No, it just worked. Oh, because we have defer. That's right. If we don't do defer, save it, it probably won't even compile. Oh no, it compiled. It's just segmentation fault because we tried to access memory that we just freed already. So it'll be like, oh, sorry. Nope. Okay, makes sense. Exactly what I expected. So in theory, I could create memory for like a array of 300 of those, right? Or let's do what, use 64, right? We were able to make 6 million of them. Let's do 1000 times 1000 times 1000. Let's allocate memory for a whopping 1000 of them. And some number will be U64. Let's do... Can I do this or some sort of that? I don't even know. Let's see what happens. Can I difference non-pointer U64? So this is a pointer to that. I don't know that syntax yet. So again, I'm trying. Oh, there we go. It just waited for a moment and went down. Is there like sleep or something? Standard sleep? Time sleep? Let's search for it. Zig sleep. Standard time sleep. I didn't see it there. Standard time sleep. Referenced by this. Wait, what? Root source file struct has no member. Yeah, they must have moved it. Language reference. This is long things. Come on. Find sleep. We have a video. Oh dear. The term zig sleep can refer to this pausing execution, similar to sleep functions. How do I sleep for certain time? Whatever, pause execution in Zig. What the hell? How hard is it to find it? Standard time sleep. Nope. 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 It does not exist. Come on. Micro and time, whatever. Do they want to force me to go through a horrible time of finding, what do you call it? Just making a while loop? Constant start is standard time, whatever, timestamp in seconds. Not in seconds. Milliseconds. Good enough. And that will be that. Then we do while. So let's do var. Current will be the same thing. Okay. So while current, while start minus current, no wait, current will be larger, right? So current minus start is less than 1000 milliseconds, or let's do 3000 milliseconds, okay? And we're gonna use this fancy thing of saying that current is this. Hopefully I can do that here. And then our function body, which will be nothing. And sure. And then we just finish our defer. Will that work? Run. Thinking, 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 thinking. And we finish. Okay, so this works. I just want to see how much memory that uses. What if I'm gonna run it? OBS memory to 7 gigabytes? Wow. It went to 7 gigabytes. Seriously. Can we do 10 times more? Let's add a 0. That should be 70 gigabytes, right? Run. 13 gigs, 30 gigs, 48 gigs, 64 gigabytes, 74 gigabytes. Okay, wow, this is using a lot of memory. How easy it is to just go overboard, right? I don't want to go too high because it's gonna go swap and I know stream will fail. But holy moly. And all it is, it's what? 10 billion U64 values, and that's it. Huh. That is very surprising. That doesn't make any sense. Because what? You can have Minecraft world is so much larger, right? I mean, they must be using crazy compression there, like, you know, to skip everything, whatever. But they also store way more data than just U64 per block, I'd suppose. Or maybe they're not, I don't know. But this is literally one instance of it, right? So I am very confused. Why is it that it uses so much memory? Because 1000 of that should be nothing, right? I'm gonna run it and it should be tiny. 1 megabyte, I guess that's just a stack, right? I'm gonna add 2 zeros to make it 100,000. 1 meg, still. Wow, this goes slowly. I'm gonna go to a million, and maybe we're gonna get to 2 megs? 8 megs, okay. So if I was able to fit 6 million of those in a stack, that means that the stack was like several megabytes? Something doesn't add up for me here. I am not sure why I'm surprised by those numbers. Let's say million, right? A million elements. And what? A 32-bit value is 4 bytes. So in this case, it'll be a full 8 bytes, right? For a 64-bit something. So we've got basically 8, 8 million. That's how many bytes we're dealing with. Oh, so that will be close to 8 megabytes. Okay, all right. So the moment we get, because these are bytes, kilobytes, megabytes. So if we're gonna slap on another 3 zeros to make it 1 billion, and we just put 8 in there, so that'll be 8 gigabytes. Okay, that makes sense. Huh. Okay, it doesn't lie. So if we did 7 with an extra 0 at the end, that was 70 gigabytes. All right, and probably some kind of overhead above that. Interesting. Alrighty. Let's get back to our actual content. Enough of playing around with using up too much memory. All right. So why useful? While useful, you might want to use C allocator, which is an alias to the C standard allocator, malloc. So yes, you can use malloc and zig if you want to. Just use the C allocator from the zig standard library. However, if you do use calloc, you must link to libc when compiling your source code with the zig compiler by including the flag -lc in your compilation process. If you do not link your source code to libc, zig will not be able to find malloc implementation in your system. Okay, makes sense. Alrighty. So now we go to the page allocator. So I'm not sure what that is. The page allocator is an allocator that allocates full pages of memory in the heap. What is a page of memory exactly? In other words, every time we allocate memory with page allocator, a full page of memory in a heap is allocated instead of just a small piece of it. The size of this page depends on the system you are using. Most systems use a page of 4 kilobytes in a heap. So that is the amount of memory that is normally allocated in each call by page allocator. That is why page allocator is considered a fast but also wasteful allocator in Zig, because it allocates a big amount of memory in each call. And you most likely will not need that much memory in your program unless you write the this program, right? We got 2 megabytes and we got 1 gigabyte of memory. So if you would divide it by 4 kilobytes, that will be a lot of pages. And I guess for some kind of larger lists of or long text, something that you can grow a lot fast, it would make sense, right? Because the thing with lists is that every usual implementation of a list that lives in a heap is that it allocates certain amount of memory, and the moment you exceed it, you add more than what it was allocated for it, it's just gonna be, you know what, I'm gonna request twice as much memory now, and therefore it needs to allocate that memory and copy whatever the list was to a new location, and that's that. So, yeah. Something like a page allocator would be great because it could, in theory, maybe in theory make it a little bit less wasteful. I don't know. Interesting. So then we have buffer allocators. Yeah. So then it's too bad that they don't even like specify like what would you use it for. Give us an idea. Like really nothing. Then we have buffer allocators. The fixed buffer allocator and thread safe fixed buffer allocator are allocators objects that work with a fixed size buffer object in the back. In other words, they use a fixed size buffer object as the basis for the memory. When you ask these allocators object to allocate some memory for you, they're essentially reserving some amount of space inside this fixed size buffer object for you to use. This means that in order to use these allocators, you must first create a buffer object in your code and then give this buffer object as an input to these allocators. This also means that these allocators objects can allocate memory both in a stack or in a heap. Everything depends on where the buffer object that you provide lives. But if you want to give it off to a different thread, you won't be able to give your pointer to a stack because, as far as I know, each thread has its own stack unless you can somehow link to them. Maybe you can. That'll be interesting. If this buffer object lives in a stack, then the memory allocated is stack-based. But if it lives in a heap, then the memory allocated is heap-based. In the example below, I'm creating a buffer object on the stack that is 10 elements long. Notice that I give this buffer object to the fixed buffer allocator constructor. Now, because this buffer object is 10 elements long, and this means that I am limited to this space. I cannot allocate more than 10 elements with this allocator object. If I try to allocate more, the alloc method will return an out of memory error value. So we have buffer of 10 U8. And for each element, I initialize to 0. Then we get our fixed buffer allocator and init with a pointer to this. Okay, so I guess we need to give it, I guess it would expect U8s. And we have allocator, blah, 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 and we can try to allocate that much, and there we go. Remember, the memory allocated by these allocator objects can be either from the stack or from the heap. It all depends on where the buffer object you provide lives. In the above example, the buffer object lives in the stack, and therefore the memory allocated is based in the stack. But what if it was based on a heap? As we described in section 3.2, one of the main reasons why you would use the heap instead of a stack is to allocate huge amounts of space to store very big objects. Thus, let's suppose you wanted to use a very big buffer object as the basis for allocator objects. You would have to allocate very big buffer object on the heap. The example below demonstrates this case. So here he creates basically 100 megabytes of memory. There we go. We deferred the freeing of the heap allocator, right? Of the memory buffer itself. And then we just say, hey, initialize with this. Our allocator is, look at that. So we initialize this whole fixed buffer allocator. And then from that, we return the allocator. Oh, because allocator itself, like this thing, I guess it's a standard thing. It shouldn't take anything. Okay. So we could, in theory, pass those around if we wanted. And hey, give me a space for 1000 U8s, right? Allocator free input. Yeah, we need to free that one as well. Alrighty. Standard heap page allocator. Okay, all right. So because we use the page allocator here to do this, to get it on a heap, and then we just did fixed buffer allocator or whatnot, and it manages it further. Wonder what exact use cases are for those, the guardrails or something. And finally, we have the arena allocator. The arena allocator is an allocator object that takes a child allocator as input. The idea behind arena allocator in Zig is similar to the concept of arenas in the programming language Go. It's an allocator object that allows you to allocate memory as many times you want, but free all memory only once. Oh, that's what it is. In other words, if you have, for example, called 5 times the method alloc for an arena allocator object, you can free all the memory you allocated over 5 calls at once by simply calling the dinit method of the same arena allocator object. Okay? If you give, for example, a general purpose allocator object as input to the arena allocator constructor, like an example below, then allocations you perform with alloc will actually be made with the underlying object general purpose allocator that was passed. So if an arena allocator, any new memory you ask for is allocated by the child allocator. The only thing that an arena allocator really does is help you free all memory allocated multiple times with just a single command. In this example below, I called alloc 3 times. So if I did not use an arena allocator, then I would need to call free 3 times to free all the allocated memory, right? Alloc, and whatever. Okay. So the alloc, and defer the init of the AA because this is an arena allocator. Yeah, so it will free them for you. Okay, but considering it's still a standard allocator, you could deallocate them one by one, right, to regain some memory. But I can see it working in a fashion of being maybe just a safety precaution. Like, you know what? Let's just make sure that we always free something, and therefore you can just make sure. Or maybe you have some situation where it will be difficult to handle some situations where maybe during an error or something, there might be a situation where you lose some, where it will be basically difficult to free some stuff. And you're like, you know what, in case of error, just exit here and at the end call dinit on the entire allocator, and that will just fix it or whatnot. Okay, this is fun. It just keeps track of pointers for you, I guess, and that's it. Okay, the alloc and free methods. In the code example below, we're accessing the standard in, which is a standard input channel to receive an input from the user. We read the input given by the user with the read until delimiter or end of file method. Now, after reading the input of the user, we need to store this input somewhere in our program. That is why I use an allocator in this example. I use it to allocate some amount of memory to store this input given by the user. More specifically, the method alloc of the allocator object is used to allocate an array capable of storing 50 U8 values. Notice that this alloc method receives two inputs. The first one is a type. This defines what type of values the allocated array will store. In the example below, we are allocating an array of unsigned 8-bit integers, U8. But you can create an array to store any type of value you want. Next, in the second argument, we define the size of the allocated array by specifying how many elements this array will contain. In the case below, we are allocating an array of 50 elements. So we, I guess, can look at it. We have allocator and alloc U8 50. So we just space for 50 of them, right? Oh. And that means it will return index to the first element or an array. Very curious. What's going to happen here? So allocator alloc will return an array. It didn't return pointer to an array? What? So type and how many? And I guess we... Okay, this is the confusing part because I would expect that I would say, hey, we have 50 elements of this. But now I'm making a list of 50 of the array. Again, not pointers. I'll do this and what were we using before? Alloc. Yeah. Let me just undo some stuff here because I am getting confused. Oh, we did create. Oh, that's what it is. Create. That's what we're using. So this is some kind of alloc. The method alloc of the allocator object is used to allocate an array capable of storing 50 values. But we didn't get a pointer unless array itself is considered a pointer. So notice that this alloc method receives two inputs. The first one is a type. This defines what type of values the allocated array will store. In the example below, we are allocating an array of unsigned 8-bit integers, but you can create an array to store any type of value you want. Next, in the second argument, we define the size of the allocated array by specifying how many elements this array will contain. In the case below, we are allocating an array of 50 elements. Hello, CPN. How's it going? It's going well. How about you? You can explain something to me straight away. I already have a question for you. Because in some code examples, I was creating using allocator create, and that gave me a nice pointer to this array, which is great. Okay. And now I'm going through an example of the alloc. So when I copy this magical code, I can see that this alloc says, hey, create me 50 elements of U8 and returns an array. It doesn't return a pointer to an array. So from my perspective, it's like, wait, this just created memory in the heap and copied it over into the stack? Unless array itself is already a pointer that I pass it around magically? What if I'm gonna say yet one? What if I'm gonna skip this? CBN says it returns a slice. Oh, okay. And the slices basically hold the pointer inside, so every time I'm moving it, slices lives on a heap, slice itself lives on the stack because it holds just a pointer and from where to where. And that's all it is. So it's a magical pointer that points at this type of data. Okay, that makes sense. Thank you. That's actually awesome. So instead of having a pointer that, in our case, all right. Huh, okay. This will be interesting. Alrighty. But you can create, store any type of value you want. Yeah. In section 1.8, we described that strings in Zig are simply arrays of characters. Each character is represented by U8 value. So this means that the array that was allocated by the object input is capable of storing string that is 50 characters long. So in essence, the expression var input U8 50 undefined would create an array of 50 values in the stack of the current scope. But you can allocate the same array in the heap by using the expression whatever allocator alloc bam. So now I'm confused. Because this doesn't have defined anything in the brackets. That's how we know that it's a slice. Okay, makes sense. All right. And CPS slice isn't much different from array. If the length is known, at compile time it becomes an array. Yeah, I mean, I just imagine a slice to be something like a struct. What are struct slice? I don't know if that's gonna be problematic. Whatever. I forgot how to make slices, but whatever. I mean, struct. I would expect that this will have some kind of array pointer that points to, in this case, U8 specifically, where the array begins or whatnot. And then it has start index, which will be, I don't know, some kind of number, probably U size. And then it's gonna also have the end index or something like length, which will be also U size. Right? That's what I imagine it being. But this is what a slice is. And it's a teeny struct that you just pass around. At least I know that's how it works in NIM, because they actually bothered explaining that. CPN says no start index, just pointer and line. Okay, so just pointer to the thing. All right, makes sense. So our array element pointer, that's what it is. Okay, I guess that will explain why you can't grow the slice. You can only make it smaller, right? Okay. Alrighty. Yeah, so we have this whole thing, allocator, allocate this thing, we defer the freeing of it, and then we can iterate over everything and it initialize them to 0, and then we can input reader is standard in reader, and we try to use it to read until the limiter, and we just give it input as the buffer to write to. Okay, and that's it. Okay, all right. Also notice that in this example, we use the defer keyword, which are described in section blah blah, to run small piece of code at the end of the current scope, which is the expression allocator free. Well, we saw something similar to that like 10 times above it, so wow. And when you execute this expression, the allocator will free the memory that is allocated for the input object. We have talked about this in that section. You should always explicitly free memory that you allocate using an allocator. You do that by using the free method of the same allocator object you use to allocate this memory. The defer keyword is used in this example only to help us execute this free operation at the end of the current scope. NCPN says, by the way, you can configure that allocator to log every time an allocation happens. Oh, that's fun. Cool. A little debugging tool, right? Among other options. Okay, it would be fun if you could pass it a function to call every time an allocation happens, but I guess it'll be easy enough to write your own wrapper for an allocator that also acts as an allocator that maybe allows you to hook into things. That would be fun. All right. So we learned about the alloc and free, and now let's learn more about the create that we actually saw the first time. With the alloc and free methods, you can allocate memory to store multiple elements at once. In other words, with these methods, we always allocate an array to store multiple elements at once. But what if you need enough space to store just a single item? Should you allocate an array of single element through alloc? The answer is no. In this case, you should use the create method of the allocator object. Every allocator object offers the create and destroyed methods, which are used to allocate and free memory for a single item respectively. So in essence, if you want to allocate memory to store an array of elements, you should use alloc and free. But if you need to store a single item, then use the create and destroy. Okay. Sure. Why that difference? I guess it's just an API that one takes a slice, right? And this one just takes a pointer. In the example below, I'm defining a struct to represent a user of some sort. It could be a user for a game or software to manage resources. It doesn't matter. Notice that I use the create method this time to store a single user object in the program. Also notice that I use the destroy method to free the memory used by this object. Okay. So create, I guess, is a little bit more low level, I presume. So let's get to our previous example. After I get rid of this thing. There we go. So here we had the general purpose allocator. I just want to look at the same thing because here we have what 1 billion elements, right? 1 gigabyte. So I wanted to go to 70 again, all right? And now I want to see if there will be any difference in amount of memory allocated between create and the other stuff. I will be very surprised to see some. I just really want to see some. I'm curious. I'm not used to this level of stuff, so I kind of feel like a kid enjoying stuff. How much I can zoom it in without compromising on stuff? Not much. But I can do this and that, and maybe I can zoom in more. So again, I guess our program will show up here, right? We run this, and where'd it go? Error. Allocator const byte row alloc alignment error. Wait, out of memory? What happened? What changed? 1000 times 1000 times 1000, 10, and 7. What is that task manager? It's htop. How is it too big? I had that last time. It was 1000 times 1000 times 1000 with a 0. And I guess I did 7, right? Let's do this. Times 1. Save. Run again. I mean, gross 7 gig. Yeah, exactly, 7 gigabytes, and that's it. No big deal. Or maybe I did it like something else, but I should be able to do 70, no problem. This is confusing me now. And now it's already complaining, too large. What the heck? Why did it work before? can I do a bunch of more undos until I get something? Yeah, that was the thing. Undo, undo. We got this. We at some point were running some calculations. Right, we had our timestamps. We got to here, that was 7 gigabytes. But I recall, whatever. This is weird. I don't know why it's behaving different this time. But we got to 74 gigabytes of memory use, so yeah, maybe it just doesn't like that big number anymore. I don't know. It's very, very, very confusing at this point. Very confusing. What if I run this 70 times? That would be interesting exercise. Variable of pointers, which is something that will hold 70 of, what is it? 70 of pointers to to what is it? To array of 1 billion of U64. What the heck? Wait, that's type, which is, how was initialization? There we go. Okay. And CPN says if you do this in C, it won't actually allocate memory unless you use that memory. Interesting. CPN says, okay, I'm a bit busy. See you later. Alrighty. So we get pointers. Now we can do 4 and was 0 to 70. Right. And we're gonna do it I in here. And what we need to do is basically whatever, some number. We can just copy this whole line, throw it in here, right? And basically say pointers I is some number. Okay. And why does it calculate to 1000? What the heck? This is confusing. All right, so we do that. Yeah, the same thing here. It just calculates to 1000. Very, very confusing. So we do this, and we basically need to do we need to defer everything, but we don't need to defer. We can just literally run it at the end, which will be for, again, 0 to 70. We're gonna just call this draw and everything. We're just gonna do allocator, destroy, and we need to basically extract from pointers. Take this, and there we go. So no deferment, some number. I guess that's just to use that memory, right? So in theory, we could already plop it in here. That's some number at this point added there, right? And I hope this constant here won't be a problem because it's just a pointer. And then we start this thing. So let's start with 1. I mean, like 2. Or let's actually do it here. Constant count is gonna be 1. And can I just do plop it everywhere I see 70? Seems like. So let's start with 1. See if this even runs. No, error. Expected 1 or elements found 0. Wait. Oh, it wants us to actually define them all? Uh-oh. I see. So can we just do this and wait, because this is just that. So in theory, I could say, hey, this is type of this and undefined, right? And then we're gonna allocate them here anyway. So I guess it's gonna work. Let's try it. Oh, it did something, right? So let's try it again. Up to 7 gigs. Why was it 7 gigs? Do I have number 7 somewhere? I allocated it once. What the heck? I run it and goes all the way to 7 gigs. Okay, this is confusing. 1 billion should be 1 gigabyte. Oh, because it's times 8. Now. Oh, it is times 8, right? That's what it was. That's why we weren't able to create more. Oh, that makes sense. But hey, at least we did some fancy code to do stuff. So if I'm going to make it 10, it's gonna go nearly 80 gigabytes, right? So now I'm gonna do this and hopefully it's gonna release some memory, right? We go 13 gigs, 30, 48, 66, 74 gigabytes. Now it's thinking. So this whole allocation took so much time and then it goes back to normal. Okay. All right. So yeah, that worked. 74 gigabytes. So now the question was, what if instead of doing it that way, we're gonna switch it to use the allocant free. So to do that, we would expect that we have the number that we're gonna store of slices of U64. Okay. We won't be storing anything else. We will be storing slices. Therefore, some number won't be this anymore. We're gonna do alloc. We're gonna say that we want to use 64, and in here we have our number of them. Okay, so this should be already 8 gigs or something. And sure, we can rename it from pointers to slices because that makes more sense. And we add a slice here. We allocate some data to there, so we don't need to do any, what do you call it, dereferencing or anything. But this being const might be problematic now, right? I don't know. And then we're gonna wait our time. And then instead of destroy, will be free. And this slice, right? So let's see if that works. Okay, we've got an error. no field or member function named allow. Alloc, right? What? Where did W come from? Run. There we go. 11 gigs, 29 gigs, 47, 64, 74. Okay, so it stayed pretty much at 74. And suddenly tells me it's the same speed or whatever. Okay, alright, alright. That worked. My curiosity is satisfied. We're able to use both, and this definitely is more pleasant to use because we don't deal with any like explicit pointers, so that's fun. Okay, alright. So we're nearly done with this whole thing today, right? We did the create and destroy. Beautiful. Oh, and we actually did the finish. Okay. Wow. We finished roughly exactly when my time is up. Okay, I guess that'll be it for today. I'm very happy with I'm happy with this introduction. It's kind of lacking, but at least we know that we have allocators. They return type that we instantiate from which we can create an allocator. So it's kind of confusing how it's set up, but I'm sure there's a specific reason behind it. And yeah, and I guess we can create however many allocators we want. It just doesn't matter. Maybe they're even all static, pointing to the same thing. Who knows? But yeah, this was fun, and I'm looking forward to the next thing, which would be actual project. And again, this is a lot of text. Okay, all right. So this will be fun. Looking forward to it. It'll be next stream. Don't know when exactly. Kind of busy recently. So yeah, thank you for watching. I hope you learned something just like I did. And see you next time.